Power series, part 3. Can you differentiate and integrate a power series? Let's go ahead and start with where we left off, and let's take a look at the basic theorem about differentiating power series, which says that a power series may represent a function, and we can go ahead and figure out its derivative by taking the derivative of each term of the power series, and that'll represent the first derivative of the function. So if I want to find the derivative of this function right here, I don't have a function representation other than the power series. I can still find its derivative by taking the derivative of each term, term by term. All right, let's take a look at taking the derivative of a function. For example, f of x is equal to 1 over 1 minus 2x. We found the power series representation as long as the r, the absolute value of r, which is 2x, is less than 1. I want to find the derivative of this function. Now, we can do a derivative function using our old methods here. But sometimes power series don't have a function associated with it. In this case, it does. So this is the function right here, after I've simplified it. And this power series representation is really the derivative of each term, each one of these terms as I go through here. So the derivative of 1 is 0, the derivative of the second term is 2, the derivative of this term is, again, I go ahead and take the power rule with a chain rule and so on. So this is a representation, a power series that represents this function right here, as long as it meets the criteria there. We also have term-by-term integration. So if I have a function right here and I would like to find its integral, then all I have to go is term-by-term integration. Let's take a look at an example. So I have this 1 over 1 plus x, which I have already found a power series representation. And what I'd like to do is I'd like to be able to integrate that. And we know that when we integrate this right here, it leads to this right here, the natural log of 1 plus x. And what we're going to be able to do now is find a representation for that. And how do we do that? What we're going to do is we're going to take each one of these terms and we're going to be integrating it. And this is how we do it. We're going to integrate from 0 to x, and this is the dummy variable right here. Each one of these is the dummy variable, so I'm going to integrate each term right here, evaluated from 0 to x, and then I'm going to substitute x into all of these terms, but when I substitute 0 in here, it's not going to add anything. Sometimes it will, so that's why we have to consider the upper and lower bound right here. And so now we have a power series that represents the natural log of 1 plus x. All right, let's take a look at this these power series, the partial sums of these power series, and see how well they represent the natural log of 1 plus x. So we have this formula over here, and we're going to take each term one at a time. So this is the first 2 terms, and then the first 3 terms, and then the next 4 terms, and we're going to graph them, and you can see that they get closer and closer to looking like this function right here. And from here, from -1 to 1, because that's the requirements of the 1. And the more terms you add, the closer and closer it looks. Okay, time to use the calculator. So now we have a representation for this, and we'd like to use our calculator to see if we can approximate the natural log of 2. So the natural log of 2 will be the natural log of 1 plus 1. This is my x. So now I'm going to, everywhere I see an x, I am going to write the number 1 because that's what I'm substituting in there. So this will be 1 minus 1/2 plus 1/3 minus 1/4 plus, and so on and so on. And so that's what we're going to do. Now in this page it shows how you can do it by avoiding the sequence mode, and I want to show you how we can use the sequence mode. So again, I'm in sequence mode, dot. I'm going to go to y equal, and I'm going to show you that we want to find the first partial sum. The first partial sum is going to be 1. The second partial sum will be 1 minus 1/2, which is 1/2. The third partial sum will be 1/2, and then I'm going to add 1/3, and that's going to be 3/6 plus 2/6, so that's 5/6. And then the sum of 4, and so on. It's just going to keep adding those all together. And the way we do that is we find the sum right here, and you can get that sum by doing this. Second list, and then you go over here and you can see the sum there. And that's how I got the sum. I found 5. Okay, now I'm going to go back to y sub 1. So that's how I got the sum. And then the sequence that I got afterwards, I went second list, and I went over here and I got my sequence right here. So what it's doing is it's going to be adding. And I'm going to go back here, y equal, and I'm going to continue here. And I wrote -1 right here. They're showing us -1 to the n. Now the first term, I didn't put n, I wrote n minus 1. I'm going to start at 1, but I need this first term to be positive, and so I didn't want that to be a negative term. And then I wrote divided by n, which is just really this 1 over n. Actually, I could just go back here and insert 1 divided by 1 over n. So I'm taking this -1 to the n power, and all these numerators are all 1, and this is going to be 1 over n. And I'm going to continue so you can see. My variable is n. I'm going to start from 1, and I'm going to go to n, and then it asks for the minimum 1, and I have my parentheses. So my first term, my first partial sum is 1. And then I'm going to go to my window so you can see my window. And I'm graphing from -1 to 4. And then I'll hit graph. Now I'm going to hit trace. Oh, it's still working. Trace. At n equal to 1, remember I have a sum of 1, and then my sum is 1/2, and then my sum is 5/6. I have that 5/6, and so on. And so it keeps on going, and it gets closer and closer to, and it should be natural log of 2. So as we get closer and closer, we'll get close to that 0.69. And you can see here in the reading, it takes a lot of entries to get this close to the natural log of 2. Okay, so the natural log of 2 is equal to this series of constants. All these constants are being added up together. Okay, let's use integration to find a power series that represents tan inverse x. All right, so I know what 1 over 1 plus x is. Here's the power series that we've talked about before in a previous screencast. Now I want 1 over 1 plus x squared. Well, all I'm going to do is substitute x squared in here because that's what my ratio is going to be. And so now here's my representation for my power series for this. Now tan inverse is actually the integral from 0 to x of this expression, 1 over 1 plus t squared dt. Again, this is a dummy variable I have to have. Well, I can replace this with the power series, and I go through term by term integration, and from 0 to x, and then I get this. And this is the power series representation